Hello. In today's video, we will finish our study of Chapter 7. We are only covering up to 7.2, estimating a population mean. This section will be very similar to the one before it, in that our main goal is to use the sample mean x bar to make an inference about the corresponding population mean mu. We're going to use the same methods for p and p hat that we're going to use now for mu and x bar. We'll see what we mean. If I want to build a confidence interval and find a margin of error, we're going to need these three ideas of a point estimate, the confidence interval itself, and then the sample size, which we'll find later on. Again, the point estimate is the value that will point more clearly to the population parameter. In this case, the sample mean, x bar, is going to be the point estimate, the single value estimate that will give us a good approximation for the population mean mu. Our confidence interval, again, will build to try and encapsulate where the true population mean is. Then, if we want to design a poll or some sort of question, we'll be able to find the number of people necessary to estimate the population mean correctly. Okay, our initial goal is going to be to construct a confidence interval used to estimate the location of the population mean. So just like in the previous section, we want some notation. Mu is going to be our population mean. X bar is going to be our sample mean. N is going to be the number of values of the sample. E will be our margin of error, and S will be our standard deviation of the sample. This is going to be a slightly different way of doing things. First of all, we're going to try and estimate the location of the population mean. What we will assume is that we do not know the standard deviation of the population. The second thing that will come up is here we have a number of values again, n. And what is going to be different about the mean is, remember, the mean is a sum. Normally, it's a sum of all the x values divided by the total number of things. When we go to estimate our margin of error, what ends up happening is the number of things will play a larger role for the mean than it will for the proportion. That idea is going to be what we call a degree of freedom. It doesn't matter when we get to it if we completely understand what it is. All that matters is we understand how we apply it. So the requirements for us to be able to estimate a population mean are going to be very similar in that we need to have a random sample and that we need to be normally distributed or have at least 30, have a sample size of at least 30. These things will be satisfied for us automatically. I won't make you go through it. But because, like we said above, that when we're computing a mean normally, when we're regularly computing a mean, right, we need to know the number of people or the number of objects. And so it turns out that if we want to estimate the location of our mean, that we kind of actually end up needing a different distribution. We're not going to use the normal distribution. We're going to use something else. So our margin of error is going to be E equals T sub alpha of 2. And this will get to, this is called the student T distribution, times S, which is our sample standard deviation, divided by the square root of n. And again, it says use the degrees of freedom being n minus 1. And I know this doesn't mean anything to you right now. It will in a second. Again, when we look to build our confidence interval, we need a confidence level such as 0.95 or 95% confidence. And again, we're going to yield some unconfidence level or an alpha level that's corresponding to that. In this case, a 95% confidence level gives us an alpha value of 0.05. And again, as you said, an alpha over 2 value of 0.025. So let's continue. So the critical value we have now is not z sub alpha over 2, it's t sub alpha over 2. It's the critical t value, again, separating an area of that alpha over 2 in the right tail of what we call the student t distribution. And the student t distribution is one we use when our population standard deviation is unknown, right? The normal distribution, we need to know a mu and a sigma. But if this sigma is unknown, the question is, where do we go from here if I don't know my standard deviation? And that's what the student t distribution is. To account for that, we need to use what's called a degree of freedom. And it does not matter exactly what that means. All we need to know is that the number of degrees of freedom is always n minus 1. It's always one less than the sample size. So for example, if our sample size was 50 people, the degrees of freedom we would use is one less, of 49. Okay, this will come up a little bit more in chapter 8, but we might as well define it right now. If a population has a normal distribution, then we can adjust it by taking x bar minus mu divided by s over root n, which kind of looks like the central limit theorem. But if we let that be our t value instead of z, that is going to be our student t distribution. And it will work for all samples of size n. We commonly call the student t distribution just the t distribution. Again, the way we're going to compute our critical value of t sub alpha over 2 requires what's called the degrees of freedom. And the degrees of freedom are the number of sample values that can vary based on a certain number of restrictions that are imposed. And all we need to take away from that is that the degrees of freedom for our examples will always be n minus 1. So the question in the previous section was, how do we find our critical value z sub alpha over 2? And that's going to be the same question we have here. How do we find our critical value of t sub alpha over 2? How do we find this value? Well, what we're going to need is a new table, table A sub 3, which is included in Blackboard. And what we want to do is look at two different parts of this chart. We want to look at the value of alpha over 2, and we want to look at the number of degrees of freedom. Here is table A3, the list of critical t values. What we'll see is in this first row, we get the area in one tail, which for us will represent our alpha over 2 values. Here in the second row, it gives us the area in two tails. That is the actual alpha value itself. And we should see the values on top of each other here. This top value is exactly 1/2 of this bottom value. Going down this side, we see the different degrees of freedom. So if I want to find a t sub alpha over 2 value for having a 95% confidence interval and n is equal to 30, all we're going to do is take that 95% confidence level, realize that that means that alpha is 0.05, and my alpha over 2 is 0.025. That tells me my area in one tail is 0.025. That means I only want to look down this column. Because n is 30, that tells me my degrees of freedom is going to be 30 minus 1, or 29. So to find my critical value, I'll go to the 29th row in that middle column right there. So my t sub alpha over 2 in this problem will be 2.045. What is unusual about the student t distribution is there is not a single student t distribution, but many student t distributions. Because the fact that the number of items in our sample makes a difference, we can get multiple student t distributions depending on the degrees of freedom, depending on the size of our sample. And so here is just a quick example of what in blue a student t distribution may look like if there are only 3 items. This kind of reddish one looks like if there are just 2 or 12 items. And the green is an actual normal distribution. And some key points about it we should see is that the student t distribution is still a symmetric bell shape. It also, the distribution itself has a mean of 0. This will not come up as much, but it still kind of looks like the normal distribution. And lastly, as the sample size gets larger, as n gets bigger, the student t distribution actually starts to get closer to the standard normal distribution. And we can see that above, right? If blue is the student distribution with n equals 3 and red is with n equals 12, the fact that 12 is greater than 3, that red line starts to look a little bit more like the green normal distribution line, that they do start to actually become closer together. Okay, let's construct a confidence interval for the population mean. If we don't know our population standard deviation, which is normally the case, we'll have to rely again on our t distribution and our degrees of freedom that we can find in table A3. What we'll do is we'll compute the margin of error using this margin of error formula using t sub alpha over 2, right? We'll actually have to find that critical value. Then, just like in the previous section, if I want to estimate where my population mean is, I will use my sample mean and subtract our margin of error for a lower bound and add our margin of error for an upper bound. And again, we'll get a range of values just like we did before. So let's find the critical value, t sub alpha over 2, that corresponds to a 95% confidence level, given we have a sample size of 15 people or 15 items. Again, because we have 15 items, our degrees of freedom is going to be 14, which means when I look at my chart, I want to look at the row that has a 14 in the first column. And again, if we want to be 95% confident, that means alpha is 0.05 and that there's an area of 0.025 in each of the tails. That's what it means by area in one tail of 0.025. In each of our tails, there's a singular area of 0.025, but combined, there's a total area of 0.05. So let's look at our table A3 to find the critical value for this example. Okay, we got our degrees of freedom being 14, and we got our alpha being 0.05, which means I want to be in this column, area in two tails of 0.05, and this row because my degrees of freedom is 14, which tells me my critical value of t sub alpha over 2 is going to be 2.145. Notice this is different than the critical value we computed above because the critical values using the t distribution are completely dependent on the degrees of freedom. This would be the critical value using a degrees of freedom being 14. Okay, let's do an example. Suppose a list of 15 birth weights of babies born on a specific day in March have a sample mean of 30.9 hectograms and a sample standard deviation of 2.9 hectograms. We're going to construct a 95% confidence interval for the birth weights. The first thing we have to do is find our margin of error E, which is t sub alpha over 2 times s over the square root of n. So in this case, the first thing we really have to do is find our critical value t sub alpha over 2. Because n is 15, that tells us our degrees of freedom is 14. Because I have a 95% confidence interval, that tells me alpha is 0.05, and my alpha over 2 is 0.025. And we computed this already. We found that critical value. That was 2.145. So I can compute E, which is going to be 2.145, times my sample standard deviation, which is 2.9, divided by the square root of n, which is the square root of 15. If I compute this, I get 1.606, keeping that 3 decimal places as my rounding. So to construct my confidence interval, I'll have to take my sample mean and subtract my margin of error, which is going to be 30.9 minus 1.606, which becomes 29.294. And my upper bound for my margin of error is going to be my sample mean plus my margin of error, which is going to be 30.9 plus 1.606. That's going to give me a value of 32.506. So my final answer, my confidence interval, will be 29.294 to 32.506. And there we've constructed our confidence interval. Okay, the next type of problem we want to solve, just like before, is trying to determine the sample size required to estimate the value of a proportion mean. In this case, we will have the population mean mu, the population standard deviation sigma, the sample mean x bar, our desired margin of error e, and z sub alpha over 2, the z-score separating an area of alpha over 2 to the right tail of our standard normal distribution. And one thing we should notice is that when we're guesstimating our sample size, we move back to z, our normal distribution. And why might that be? If we recall, our t distribution depended on n, right? It depended on knowing how many things were in our sample. Well, if we're trying to find our sample size n, there's no way I can use it for my distribution t. So we have to rely on a distribution that is independent of the number of items in my sample, which is why we move back to z and the normal distribution here. If I want to find a sample size required to estimate the population mean, I'll use this formula. N is equal to z sub alpha over 2 times sigma divided by my margin of error E, all squared. Again, because n represents the number of people or number of items I need in my sample, I'm going to always round this number up to the next whole integer. I don't use my typical rounding rules of rounding down or rounding up. I always round up for this case. Now, one thing might seem unusual in that we're trying to estimate our population mean. However, we were told that one of our parameters we were going to use is our population standard deviation. What is the likelihood of knowing the standard deviation and not knowing the mean? It turns out that that doesn't happen very often. However, there are 3 things we can do to try and estimate this. One is use the range rule of thumb, which says the standard deviation sigma should be about the range of values divided by 4. Right? We've computed this in class and we saw it does an okay job of estimating the standard deviation, but it's not great. Second, and one that we will use much less frequently, is if you're actually in the process of conducting a study, maybe you can compute the sample standard deviation. And if you take a bunch of sample standard deviations, we can use those to estimate our sigma. Lastly, maybe an earlier study may have already estimated sigma And that way, we can use that value, that old estimate of sigma. Those are three ways to get around this problem. Okay, so let's find a sample size needed to estimate the population mean. So assume we want to estimate the mean of IQ scores for the population of statistics students. How many students would we need to randomly select for an IQ test if we want a 95% confidence interval and the sample mean to be within 3 IQ points of our population mean? So if I want to be 95% confident, that means I have an alpha value of 0.05 and an alpha over 2 value of 0.025. However, we're transitioning now back to the normal distribution, which means this is the area to my right. My table for the normal distribution gives us area to the left. So I want to find an area to the left of 0.9750. That would be my critical value, z sub alpha over 2. Also, E, I want to be 3. I want to be within 3 IQ points. And so all that's left to compute before we move to our standard normal table to find our critical value is to say, what is sigma going to be? Are we going to use the range rule of thumb? Are we going to take some sample values? Or maybe we could use a previously known population standard deviation. And that's exactly what we're going to do. The previously known population standard deviation is 15. For us, I will always give you a hint of whether something is known or whether you're going to use the range rule of thumb. So let's go to our standard normal table and find our critical value. So again, we're looking for an area to the left of 0.9750. And if I start to look, I'll find that value exactly here, giving us a z-score of 1.96. This is going to be our critical value in our calculation. So the number of people we need to study is going to be z sub alpha over 2 times sigma, all divided by E quantity squared. My z sub alpha over 2 is 1.96. My standard deviation we said was 15, and our margin of error we want to be within is 3. If I compute this, I'll get 9.8 quantity squared to give us 96.04. And again, because this is dealing with the number of people we want to sample, I have to round up. So I'm going to get 97 total people in my sample. Okay, we can actually estimate the population mean if our population standard deviation is known. If our population standard deviation is known, we can revert our margin of error formula back to z sub alpha over 2, that we don't need to use the student t distribution. So if we look at an example like we had previously, the one thing that will change is we have our 15 birth weights, but we'll assume that sigma, our population standard deviation, is 2.9. What this will change is we no longer have to compute that t of alpha over 2. We're going to get exactly the z sub alpha over 2, which for a 95% confidence interval we just found was 1.96. And if we do this, we'll get a margin of error, putting all our formulas in, of 1.46760. The margin of error we found with the t distribution is 1.606. So we can see that knowing our sigma gives us a slightly shorter margin of error. We won't really be doing this type of example, although I wanted you to be able to see one and have one in the notes just in case it did come up, although it is unlikely. Hopefully this was helpful. If you have any questions, feel free to contact me. We can set up Zoom office hours. If not, I'll talk to you next time.